Hello and welcome back to Ordinary Differential Equations, the video series where we talk a lot about differential equations, how to solve them and the theory about them. And in today's part 23, I finally want to show you an example how we can solve a system of linear differential equations. In particular, we will look at a 2 times 2 system which is homogeneous and autonomous. And as you might already know, this means that we have to calculate the so-called matrix exponential. However, as always, before we start with all the calculations, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, with the link in the description, you can download additional material for all the videos. Okay, then without further ado, let's start with our example calculation. And as promised, it will be an example about a system of linear differential equations which are also homogeneous and autonomous. And since it should not be too overwhelming, let's choose a 2 times 2 system. This means we have an ODE for x1 and 1 for x2. And now we could say we have minus x1 plus 3 times x2 in the first line, and in the second we just find x1 plus x2. And now the first thing you should do when you see such a system is to rewrite it as a matrix vector multiplication. Then we can just write x dot as a vector is equal to a 2 times 2 matrix times the vector x. And now we just have to check what are the entries of this matrix to represent the same ODE. So obviously we have minus 1 and 3 and 1 and 1. And as always, this matrix we will call A in the following. And then you know that the solution set of this system of ODEs is given by the matrix exponential of A. More precisely, we just have to calculate e to the power ta, and the columns of this matrix span the whole solution set for our system. So this is a really important object, and you should know it's defined by a power series of matrices. Indeed, you just take the power series definition of the ordinary exponential function, but instead of a real number, you put in the matrix t times a. Therefore, the power, the exponent we have in this formula, now represents the standard matrix multiplication. And now the natural question would be, can we efficiently calculate all these powers such that we get our matrix exponential out? And indeed, we immediately get one answer. If we have a diagonal matrix, it's really simple to calculate all the powers. So for example, if we have a matrix B, which is given by two real numbers, and let's call them lambda and mu. Then calculating all these matrix products is no problem at all, because we just have to use the multiplication on the diagonal, which results in lambda to the power k and mu to the power k. And moreover, with that we also immediately get the matrix exponential, because everything is just happening on the diagonal anyway. So e to the power b here is given by a diagonal matrix again. Namely, as we see, we have e to the power lambda and e to the power mu. So this is simple and nice, and we can remember diagonal matrices don't make any problems at all. However, this does not help for our example, because obviously A is not a diagonal matrix. But maybe it's possible to transform A into a diagonal matrix. In fact, from our linear algebra course we know that a special class of matrices exists, and we call them diagonalizable. And the notion simply means that these matrices can be transformed into a diagonal matrix we can call D. More precisely, this is done by using an invertible matrix X and the matrix multiplication. Moreover, in the linear algebra language, we would say that A and D are similar matrices. Therefore, the important result is that diagonalizable matrices are almost as good as diagonal matrices in calculations. Indeed, we immediately see that calculating powers of A is not complicated at all. For a squared, we can just use this formula, which means we multiply A by A again. And then you see in the middle here, the X matrices will annihilate each other. And then what remains in the middle is just D squared. In other words, what we have to do here is just to calculate the power of a diagonal matrix. And moreover, by induction, we immediately see this also holds for every natural power k we can choose. So the result here is really helpful. For any diagonalizable matrix, we just have to calculate with the diagonal matrix in the end. And therefore also the matrix exponential is easy to calculate because we just need our power series representation. And then we can just use our general formula for the powers and we get x times the exponential of td times x inverse. And there we have it. This is the important result because it just means multiply 3 matrices and then we have our whole general solution of our ODE. Hence on the calculation side only 2 things remain to show, namely we have to find the matrix X and the matrix D for our given example. And there you already know, this just requires linear algebra knowledge. In particular, what we need are eigenvalues and eigenvectors of the given matrix A. It's just a 2 times 2 matrix, so finding the eigenvalues and the eigenvectors should not be so complicated. Let's start with the eigenvalues, which are given by the zeros of the characteristic polynomial. This means we have to calculate the determinant a minus lambda times the identity. So this formula simply means that we have to subtract lambda on the diagonal. And now you can use the calculation rules you know for the determinant, and what comes out is a polynomial in lambda. Indeed, in this case, after putting everything together, we get lambda squared minus 4. So I skipped some calculations, but what you see is that we get 2 eigenvalues, minus 2 and plus 2. And to keep it simple, let's call them lambda 1 and lambda 2. And at this point, please recall from linear algebra that the eigenvalues are exactly the entries in our diagonal matrix D. And on the other hand, the columns of our matrix X are given by eigenvectors of A. Therefore, in the next step, we just calculate both eigenspaces. This is not so hard because we just have to calculate 2 kernels. For the first one, we have lambda 1 is equal to minus 2, which means we have to subtract minus 2 on the diagonal, or we can just add plus 2 on the diagonal. So we just have 1 and 3 on the diagonal. And for this matrix, we still want to calculate the kernel, which is not complicated at all. Because obviously the kernel is one-dimensional and can be spanned by just one vector. And indeed we can immediately see such a vector. For example, we can choose minus 3 and 1. So we are already done with the first kernel and we can go to the second. And there with lambda 2 is equal to 2, we have to subtract 2 on the diagonal. And this results in minus 3 and minus 1. And again, this kernel is one-dimensional and we can immediately see one vector that spans it. In this case, we can just choose 1, 1. And with that we are done. We have the 2 eigenspaces and also 2 eigenvectors we can use to form such a matrix X. So in the next step, let's write down this important invertible matrix. And this is quite simple because we just put the 2 eigenvectors we have in the columns of the matrix. And moreover, we can also immediately calculate the inverse of this matrix X as well. For a 2 times 2 matrix, this is quite simple. This is 1/4 times minus 1, 1, 1 and 3. If you don't believe it, you can just calculate the matrix product to justify that this is the inverse of X. And with that, the whole process of diagonalization is done because we have found our matrix X and the diagonal matrix D. Indeed, we already know this nice formula and that D has the eigenvalues on the diagonal. In this case, first minus 2 and then plus 2. And as already mentioned before, now we can easily calculate the whole matrix exponential of A. This means e to the power ta can be calculated by multiplying 3 matrices. And there the one matrix in the middle is just a diagonal matrix with exponential functions on the diagonal. And in our case here, we just have e to the power minus 2t and e to the power plus 2t. And now you see for the calculation, you just have to multiply x inverse from the right hand side, and the solution we get out, we can multiply through the matrix X. Now I don't show you all the calculation steps because it's just a standard matrix multiplication anyway. But of course I still show you the result we get. We have 1/4 times the square matrix with a lot of exponential functions combined in the entries. For example, the first one is 3 times e to the power minus 2t plus e to the power 2t. And below that we have the entry that looks similar, but instead of 3 we have minus 1. And then in the second column we find minus 3 in front of e to the power minus 2t and plus 3 in the front of e to the power 2t. And finally the last entry just has factors plus 1 and plus 3. And that's it, and now you know we can just form a linear combination with the columns to get a solution of our ODE. Or if you want, we can also look at the solution of a given initial value problem. For example, we can take our ODE with the initial value given as the vector 0, 4. And there the solution we call alpha as always is given by a matrix vector product. Which means you just multiply our matrix exponential by the initial value 0, 4. And there you see this is quite simple because we just get our second column here. And then you see the two components of the solution are fixed with exponential functions. And there it's really important to remember that inside these exponential functions we always find the eigenvalues of our given matrix A. However, this whole procedure only works in the case that A is a diagonalizable matrix. So naturally, your next question would be what to do in all the other cases. And there I can also tell you that we already have the linear algebra tools for that as well. The correct substitution for this diagonal matrix is the so-called Jordan normal form. And indeed, how to apply this I will show you in a future video. So I really hope we meet there again and have a nice day. Bye bye.